The Physics of Interstellar Travel. Chapter 7. Relativistic Motion. We often need to take into account relativistic effects in space travel. Most obviously, special relativity is important when the spacecraft travels at a significant fraction of the speed of light. We use the Lorentz transformations to compute the motion and observe phenomena such as time dilation. Relativistic effects are also important for the rocket itself, leading to a relativistic version of the rocket equation. Even at low velocities, relativistic effects are important when we use nuclear processes to extract a significant amount of energy from matter. Finally, there are also important optical effects of relativity that become observable even at low velocities. We consider those in another chapter. Note that here we will only be talking about special relativistic effects. General relativity will not be considered. In Chapter 5, we derive the classical rocket equation using conservation of momentum in Newtonian mechanics. We can perform a similar derivation in special relativity to give the relativistic rocket equation, shown here. This gives the change in velocity of the rocket of initial mass mi when it exhausts propellant at a constant velocity ve relative to the rocket, and c is the speed of light. Comparing this to the classical rocket equation, shown here, we can see a certain symmetry. But whereas the log function increases without bound in the classical equation, the hyperbolic tangent function, tan h, is limited to be less than 1. We can see this when we plot delta v in units of the speed of light as a function of the mass ratio, shown here for different values of ve. Delta v increases for larger mass ratios and exhaust velocities, but once the rocket gets to very large velocities, further increases are limited. We can compare this to the results of the classical rocket equation, shown here with the dashed orange lines. The predictions are similar at low velocities, but deviate increasingly at high velocities. Let's consider a one-way trip to Alpha Centauri in a relativistic rocket. We start at the Earth in the bottom left corner of this space-time diagram. To ensure a comfortable journey for the passengers, we accelerate constantly at 1g. This is the proper acceleration of the rocket. The coordinate acceleration, as measured on the Earth, for example, is different, as explained in the chapter. The black line here shows the rocket accelerating away from the Earth. As we want to go into orbit at Alpha Centauri, we need to decelerate. So at the halfway point, we turn the rocket around and continuously decelerate, also at 1g. We use the Lorentz transformations to determine the motion. Having done this, we can calculate the time taken for the journey and the change in velocity achieved. Let's first consider the acceleration to the halfway point. This is 2.2 light years away, and this takes just over 3 years as measured by a clock at rest on the Earth. But because of time dilation, this corresponds to a shorter time on the spacecraft, just 1.8 years. The change in velocity is 0.952 times the speed of light. Assuming that the rocket engine delivers an effective exhaust velocity of 0.2 c, let's say, we can use the relativistic rocket equation to calculate the mass ratio required to achieve this delta v, that is, how much propellant we need. We see that this is enormous, just over 10,000 in mass ratio. This is obviously an unrealistic scenario, but it goes to show how much propellant we need to achieve a velocity much larger than the effective exhaust velocity. If we could increase the effective exhaust velocity to, say, 0.5 c, then the mass ratio required drops to about 40, which is much more acceptable. At the halfway point, as said, the rocket turns around and decelerates. The second half of the journey, shown with the orange line, is identical to the first half, just played out backwards. So the total distance travelled and time taken are twice that for the first half. Note some rounding errors here. The total delta v is also doubled, but of course the spacecraft ends up at rest, not at nearly twice the speed of light. The mass ratio required for the journey with v equals 0.2 c is 110 million, which is the square of what we would need to accelerate to the halfway point. As with the classical rocket equation, a rendezvous is much more costly in propellant than a flyby. Now, what would happen if the rocket had continued to accelerate at the halfway point instead of turning around to decelerate? Computing this, we find that the rocket flies by alpha cen with a velocity of 0.984 c after 5.28 years of Earth time, or 2.32 years of rocket time. The mass ratio is again huge, but less than the mass ratio required for the rendezvous mission. In the previous chapters, we considered rockets that use matter as their propellant, but what's actually needed is for the rocket to expel momentum. Photons have momentum, so in principle a rocket can propel itself by shining a light out of the back. Photons don't have much momentum, mind you, so it would have to be a pretty bright light. But as the exhaust velocity of the photons is the speed of light, then from the point of view of the rocket equation, it would seem that a photon rocket would be optimal. It's actually not as simple as this, because the photons have to be produced by some process. In practice, this is a nuclear or particle interaction that converts rest mass energy into photons. But these interactions rarely convert all of this energy into photons. So even though the photons still exit the rocket at the speed of light, the so-called effective exhaust velocity of the rocket is lower, and it's actually this velocity that appears in the rocket equation. We'll examine nuclear and particle processes in the next chapter, but for now it's sufficient to realize that in general, a rocket can be propelled by a combination of massive particles and massless photons. Let's see how this happens. Suppose we start with a mass dm inside the rocket. By some process, such as nuclear fusion, a fraction epsilon of this mass is converted into energy. This energy is potentially available to propel the remaining fraction, 1 minus epsilon, of the mass. Of the fraction converted into energy, a fraction, 1 minus eta, is lost, for example, to unusable particles such as neutrinos. Of the usable fraction eta, a fraction 1 minus zeta goes into the propellant photons, and the other fraction zeta goes into propelling the mass. As I show in the chapter, the effective exhaust velocity of the rocket depends on the values of these three conversion factors, epsilon, eta, and zeta. Let's look at how the velocity varies as the conversion factor epsilon increases from 0 to 1. The first case is for a matter rocket with no photons, zeta equal to 1, and no losses, eta equal to 1. The effective exhaust velocity increases monotonically from 0 to 1. That is, the more of the original mass we convert into energy, the better. Note that the limit at 1.0 is hypothetical, because if epsilon is exactly 1, then there's no propellant mass left to accelerate. The second case, shown here with the dotted line, is also lossless, eta equals 1, but now for a photon rocket, zeta equals 0, meaning there is no energy left to propel any massive particles produced by the nuclear reaction. We see that such a rocket produces a lower effective exhaust velocity than the matter rocket. It only achieves the same velocity once epsilon equals 1, as then none of the original mass goes into producing propellant mass, which would then of course not be accelerated. The Generon case involves a propellant of both matter and photons. With zeta equal to half, again without mass losses, meaning half the energy released is available for accelerating the mass and the other half goes into the photons, we get this solid line shown between the other two lines. When, in this case, 40% of the initial mass is converted into energy, that is, epsilon equals 0.4, we get an effective exhaust velocity of 73% the speed of light. Interestingly, if we introduce losses into this rocket by setting eta equal to a half, then not only do the effective exhaust velocities decrease, but the maximum velocity occurs at a conversion factor now less than 1. In reality, we cannot choose the values of these three parameters arbitrarily, because they are determined by the nuclear reaction used. We shall explore this in the next chapter. Furthermore, a high effective exhaust velocity is only part of what we want to achieve. The rocket equation tells us we also need to convert a sufficient fraction of the initial mass into propellant mass, or photons, and this is harder to do at larger epsilon. So that was just a brief look into a couple of topics where relativity plays a role in interstellar travel. We saw that relativity is not only relevant to high velocities and for modifying the rocket equation, it is also important for a slow rocket that relies on the conversion of mass into energy. In general, the exhaust from a rocket is made up of both photons and particles, which is why we refer to it as an effective exhaust velocity.